So this time we're going to go back to comparing the concepts of pathwise versus topological connectedness. Let me recall what these things are. And instead of what I did last class, which was to talk about topological space being connected or disconnected, I'm going to talk about subsets of a topological space. And then I have two definitions. To say that A is pathwise connected means that any 2 points in A are connected by a continuous path going from A to A prime, entirely contained in A. I mean, you know the formal definition, I don't think I need to write it down. Topologically connected means, and now it's a little bit different, right? So remember that we define a connected topological space, and then we say a set is connected if and only if it's connected with the related topology. So a topologically connected set is a set such that there's no subset of A that's neither empty nor everything, that is both relatively open and relatively closed, right? So connectedness means, I mean, it's again more or less the same thing as before. Basically, you're saying there's no subset of A that's neither trivial, but that's not trivial in the sense of being infinity or A, or being empty or A, sorry. There's no such subset that has no boundary, right? So that has no boundary side of it. Okay, and one thing that we saw is that pathwise connectedness implies topological connectedness. For instance, we have this criterion for topological connectedness, which is that any continuous function from A to 0, 1 discrete has to be constant. And we use pathwise connectedness to show that that's the case whenever, that we show that under pathwise connectedness, then given A and A prime, because there's a path connecting them, any function from X to 0, 1 must be constant at these 2 points, but these 2 points are arbitrary. So, we know if this connection between the two concepts pathwise always implies topological connectedness. We know that on the real line, the two concepts are exactly the same because the pathwise connected sets are exactly the intervals, which are also exactly the connected sets. So there's the two concepts are equivalent. There are examples where you have connected topological spaces or subsets that are not pathwise connected. And those examples are interesting sometimes. I mean, they're kind of a bit convoluted perhaps, but it's good to know of them. I put a sheet in the website with one such example, which is kind of the classical example. But it's also nice to know that there are natural situations in which these two concepts are exactly the same. And here's one of them. Suppose I have a norm vector space and when I say this, I'm going to assume that the topology I use here is the topology given by the norm of V. An open set, so take an open set of V according to the topology given by the norm, is connected if and only if it is pathwise connected. So I think explain what this is saying. Okay, again, pathwise always implies topological connectedness, right? So when I say connected, I mean connected in this topological sense. So pathwise always implies topological. The converse need not hold, but in this case of open sets in vector spaces, there is a converse. So what we need to show is that if an open set is connected in set V, it's also pathwise connected. So I need to somehow be able to prove that there exists paths between any 2 points of A from this simple property that A is connected. Simple meaning, the similarly, the presumably weaker property of being topologically connected. Right, how how do we do this? Perhaps even more interesting than the theorem itself is the way we prove it. And it's very typical of proof that use connectedness. Right? So we're going to assume that A is open, connected. And we're also going to assume that it's non-empty. Otherwise, it's connected trivially. And we're going to take some point that belongs to A, right, since we're assuming that it's non-empty. And I'm going to define a subset of A, which I'm going to call L, because it's supposed to be like this, which is a subset of all points in A that are they're connected by a path to A0, to A0, inside A. So we're going to show two things. So we're going to show that L is related open and closed. When I say related, I mean related to A, right? So I'm taking the topology that's induced on A. Then I can prove the subset L is both open and closed. Now, what does this mean, right? So if I know that a subset of A is both open and closed, there are three alternatives, right? Either L is empty, but that's not true because we know that A naught belongs to L. Or L is everything. And the third alternative would be that L is not A and it's not empty. But that's not allowed because we know that A is connected, topologically connected. Therefore, there cannot be a proper subset of A, right? That set that's not empty, that's not everything, that's both relatively open and closed. So once we prove this, this implies that L must be equal to A because A naught belongs to L and A is connected. So this is what we need to show. I mean, actually, this would be true always. I mean, even if A was not connected, it would be true that such subsets L are relatively open and relatively closed. But because we know that A is connected, then we can conclude that L must be equal to A. And what does that mean? It means that all points in A are connected to A naught by a path, right? So that means that the A must be pathwise connected, right? So if all points little a are connected to A naught, then we know that this relation is transitive, right? That means that any 2 points are connected, right? At the very least, if you want to connect A to A prime, you can take a path from A to A naught, and then from A naught to A prime, and you're done. Okay, so we need to prove this claim, right? So, and hopefully understand by now why it implies the theorem. How do we prove this? First of all, how do we prove that L is open? So, okay. What does it mean to be open in this case? Well, it's relatively open, right? But look, A itself is an open subset of V, right? So we showed in class that if you have an open subset of a larger space, then the relatively open subsets of A are also open in the larger space, right? So saying that L is relatively open means that L should be open in V because A is open. So let's prove that L is open. How do we prove this? Okay, it's simple, right? So given, we need to show that given an element A of L, there exists a positive radius such that this bubble, this ball around A, is entirely contained in L. Okay, how do we do this? I'm going to draw a picture and hopefully this will be enough. So we have A over here. We have A naught. And we have this point A that belongs to L, right? So what do we know about A? That it's connected by a path gamma, continuous, going from A naught to A. That's entirely contained in A. So maybe let me remove the boundary so that it's clear that A is an open set. So this guy here is open, So we know that it has a protective bubble. Some ball of radius r around it. This ball looks more like a pear than like a ball. But anyway, we know that there's this ball that's entirely contained in A. So maybe move this a little bit to the side, it becomes clear that it is entirely contained in A. And I claim that the same ball is contained in the set L. Why? We're going to use something very important, or it's easy but it's important that we proved last time. So we argued, 2 videos ago. So we argued that open balls or closed balls in a vector space, they are always convex, and therefore they are always pathwise connected, right? So if I want to prove that this ball, right, so I chose R, such that the ball is contained in A. That I know works because A is open. And now I want to prove that this ball is contained in L, right? So this is what I want to show. And I claim that the same R that I took here should work here. Why is that? So that I took here should work there. Why is that? Take a point here in this ball. I want to prove that it's connected to A naught by a path. So how do I find this path? I know that A naught is connected to A inside the set A. I also know that A is connected to any point inside the ball, right, by a path, right? There's a path completely inside the ball that connects A to A prime. Just this. But look, then there's the ball is contained in A, right? So I can replace this by saying, okay, A and A prime are connected inside A. And we know that this relation is transitive, right? So it means that A naught is connected to A. And this should be clear for the picture, right? So if I have a path from A naught to A, then I have a path to any point in the ball just by saying go from A naught to A and then from A to A prime. And that's going to be continuous as we showed 2 videos ago. So we're done, right? So what we showed is that we have this protective bubble around A that's entirely contained in the set A, and all points in this protective bubble must also be elements of L. And therefore I'm done. I said, take an element of L, and there must be a ball, an open ball, positive radius around it that's contained in L. And we showed that. Again, what does that give us? This gives us that L is open, and because L is a subset of A, which is open, L is also relatively open. It's open in the topology induced on it. So far goes so good. But we still need to show that L is relatively closed as well, right? Fortunately, that's going to be very similar, except that it's going to be easier to prove that the complement of L is open, right? We want to prove that L is closed, so we can look at the complement and show that it's open. So maybe we should. So, but we need to be careful with this stuff with complement, right? So we are looking at relatively open and relatively closed. So we should take this sort of relative complement. What do we mean by that? I'm going to show that the complement of L inside A, therefore A minus L, is relatively open. As I noticed, you don't need the relative here, right? Because if A minus L is a relatively open set, then it's also an open set of V, because A is open. And what are we gonna do with this? Well, if we know that A minus L is relatively open, then this implies that L is relatively closed, right? So it's the complements of open sets or closed sets, right? We're working with this relatively complement. How do we prove this, that A minus L is relatively open? It's actually pretty much the same proof, right? So, except that in the end the set's going to be empty, right? So we We have to stretch our imagination a little bit.
So in the end, this guy is going to be, I'm just going to repeat myself because I had a little bit glitch. In the end, this guy is going to be both, L is going to be relatively open and closed, therefore it's going to be everything, as we argued before. So we have to stretch our imagination a little bit to imagine that this set could be non-empty, right? So, okay, there are two possibilities, right? Assume first that this set is empty. Therefore, it's relatively open, it's relatively closed. There's nothing to prove about it. Now assume this is non-empty, so that's the interesting case. In the end, that cannot happen, right? But we're going to imagine that that's possible. So what is that like? So I have my set A. So it's going to be hard to imagine this. Okay, this is A. I mean, weird things happen here in the middle. We really don't know what's up here. I mean, everything, this is a place in a map, in an old map where they draw kind of sea serpents or something like that. And we know that A naught somewhere. We now take a point, let me call it A prime belonging to A minus L. And the only thing we know about A naught is that there's no path going from here to here. So somehow you cannot get from A0 to A prime by a continuous path. However, it's still the case that A is open. Therefore, there exists a small ball around A prime that's entirely contained in the set A, because A is open again, right? And now I'm going to claim the following, that in fact, the same ball with the same R has to be contained in A minus L. And I'm going to prove this with a picture, right? So this is what I'm going to show right now. But once I show that it's true, then I'm done, because I took an arbitrary point in A minus L and I showed that there's an open ball around it that's entirely contained in A minus L. Therefore, A minus L is open, right? So I need, and again, I take the ball that works for A, and this ball also works for A minus L. So it's a bit similar to what happened before. But okay, why is this true? So suppose this was not the case, right? Suppose that this ball that I took here, that's entirely contained in A, is not contained in the relative complement of L. What does that mean, right? So it means that this ball here, with radius R, contains at least one point, A double prime, this guy here, and this point has to be in L, right? So if this is not true, there's a point belonging to L inside this ball. And what does that mean? Well, this point is in L, so I know there's a continuous curve from here to here. So A naught and A double prime are connected by a continuous path. But we also know that A double prime and A prime are connected by a continuous path inside of A. It's just, well, the ball is convex, so you just take a straight line segment, right? So again, what happens? You can go from A naught to A double prime by a continuous path. You can go from A double prime to A prime by a straight line segment. Connecting the two things, you find a path, a continuous path, from A naught to A prime. But that's a contradiction, right? We said that A prime does not belong to L. Therefore, A prime is a point such that this does not happen. There's no continuous path from A naught to A inside the set A. So what I'm saying is that in order for this to be true, that there's no continuous path from A naught to A prime, it must be that there's no continuous path to any point around A prime. Because if there is such a path, you can go, to A double prime and then to A prime. So, okay, in the end, I hope it's clear. What we show is that, okay, for all A double prime in the complement of L, in the relative complement of L, there's a positive radius such that the ball around A prime is contained in A. That's just because A is open. But then the same ball is guaranteed to not have any points from L. So the same ball is contained in A minus L. And this is what you need to show, that A minus L is open, right? So, okay, we show that A minus L is open as a subset of V because all points of A minus L have a protective bubble. Now we know that A is open, so an open set of V that's contained in A is relatively open, so we know that A minus L is relatively open, and therefore the complement of A minus L inside A, which is precisely L, is relatively closed. We already proved before that L is a relatively open subset of A, is actually an open subset of V. Now we prove that it's relatively closed. We go back to the definition and we say, okay, A is topologically connected, so there's no way to have a relatively open and relatively closed subset unless the subset is equal to empty or equal to everything. But now we know it's not empty, right? Because we took this guy and this is a point of L, right? So A naught belongs to L. Therefore, L is not empty, L must be everything. L equals A, and all points in A are connected to A naught by a path. And therefore, they're all connected to one another by a continuous path. So, okay, that's it for this video. And yeah, the last thing in this section is going to be consider to give an example of a topologically connected subset of the plane, which is not pathwise connected. That's going to be in a handout. So, yeah, thanks.